So first of all, thank you for having me giving the seminar. I apologize not to be there in person. I really wanted to come, but a series of events prevented me to visit again Bangalore. I hope to have a chance in the near future. So what I want to talk about is that do we need to go beyond cold dark matter? What do I mean with that? We know that we have a very nice successful model that describes our universe, and I don't have to explain this pie chart in this conference, I guess. But I think it's fair to say that besides the 4.9%, we know very little, close to nothing, about what dark matter is, what it's made of, and even less possibly about dark energy. That didn't prevent us, theorists, to come up with a model for dark matter. And the model, which is the easiest one, if you wish, is the one based on cold dark matter. What does it mean? Cold means that there are negligible thermal velocity at decoupling. So all the velocity of the particle is given by the gravitational collapse. There is no interaction with, besides gravity, that's why it's dark, and is also collisionless. That's another assumption. That means that we don't consider a dark matter to dark matter scattering. Under this model, we have built in the past years a very successful model that describes the formation of structures. What you see here, both left and right, this is just density fields of dark matter collapsing under the influence of gravity. On the left, you have a large-scale simulation. The clock in redshift is on the top left, it's 50 megaparsec across. And on the right, you have the zoom in on a dark matter halo, one that has the mass by redshift 0 that is similar to the one we'll be hosting our own galaxy, the Milky Way. In this model, galaxy formation is a bottom-up process. We have hierarchical accretion, there are satellites colliding, and this framework is extremely successful, right? I don't have again to explain in this specific conference why it's so successful. But if you look at many papers that appear almost daily on the archive, there is a lot of people that push to go beyond cold dark matter. And usually this is motivated by the following sentence, right? Cold dark matter is very successful on large scales, but faces some challenges on small scales. And I think all of you must have heard of those problems. Now, at face value, it seems that cold dark matter has a lot of problems. They go back some to the beginning of the year 2000, like the missing satellites problem, or the too big to fail, the diversity rotation curve, the cusp core dilemma, the galaxies without dark matter. And all those problems, they always use to push to go beyond cold dark matter. So to introduce a new particle interaction field, cross-section, you name it, right? There is no shortage of models that go beyond cold dark matter. The question is that this seems to be motivated because if dark matter is facing so many problems, there must be something wrong with the theory. But now, what if I tell you that actually all these cold dark matter issues, they're not uncorrelated. In my opinion, they are just coming from a single fact. There is one source for all those problems. And the explanation, in my opinion, is very simple, is that dark matter halos are self-similar. What does it mean? Another way to see it, it means that there is no specific scale in gravity. Let me give you a visual impression of self-similarity. If I show you a density map of a dark matter halo, like the one on the left, which is a classical one, where you have a center, you have many satellites, there is no way you can tell me what you're looking at. The picture could be the host of a galaxy cluster, something that generates a lot of strong lensing, 10 to the 14 solar masses. Could be the host of a group, 10 to the 13 solar masses. Could be the host of our own Milky Way. But actually, could even be the halo that hosts a dwarf galaxy, something which has a few thousand of stars and a total mass of 10 to the 9, 10 to the 10 solar masses. And this reflects in the nature of dark matter. For example, if you look at its distribution as a function of radius, of density versus radius, all dark matter halos are self-similar. That means they all share the same density profile. Instead of talking about density profile, especially if you want to compare with observations, it's easier to talk about circular velocity, right? Circular velocity is just a recasting of mass and radius using the formula that you see there, v is square root of gm over r. Those are a bunch of dark matter halos. They range more than 4 orders of magnitude in dark matter halo mass, and you see all those profiles that are spread out. But since they are self-similar, if I rescale this profile by some typical velocity on the y and typical radius on the x, I can collapse all of them in a single profile with very small scattering. That's the self-similarity. Self-similarity also applies in the number of substructures. In fact, if you look at this plot, you cannot tell me by looking at the substructure what you're looking at in dark matter. Because no matter what, any dark matter halo always have around 300 satellites with a mass between 1% and 10 to the minus 4 of its own mass, regardless if it's 10 to the 4, 10 to the 12, 10 to the 10, 10 to the 6, you name it. Okay, that's again another issue of self-similar behavior. Why is this a problem? Well, this is a problem because galaxies are not self-similar. And that's where all the problems of dark matter, cold dark matter, come about. Galaxy properties are not self-similar. A nice way to see this was in a very nice paper by Oman in 2015. What you have on the left, there are 4 rotation curves, velocity versus radius, of 4 different real galaxies. The real points are the points with the error box, like the triangles, squares, upside down triangles, and circles. And now what you see is that those rotation curves are very different. Now, cold dark matter can fit some of them. For example, the green curve is nicely fit by cold dark matter profile. But since cold dark matter is similar, it's a stiff profile. There's no way to modify it, right? It's intrinsic to the property of cold dark matter. So when it comes to the blue points, right, there is no way you can fit it with a stiff profile because it's much shallower rays. And that's where all the problems of dark matter come about. The same applies to the substructure, right? I told you there is this self-similarity in substructures. Well, galaxy and galaxy clusters are not self-similar when it comes to visible substructures. There are roughly 50 satellites around the Milky Way, considering all the new ones discovered in the last years. But there are more than 700 galaxies around the belt 1689. So 50, 700, they are not self-similar. The number of satellites changes when you change mass. So if you want to reconcile all those problems with dark matter, you need to break the self-similarity. And how do you do that? Well, one idea, we are physicists, right? So one idea, you need to bring a scale into the problem. This scale could be, for example, a cross-section if you have self-interacting dark matter. This scale could be in axion dark matter, sometimes called fuzzy dark matter. It's the de Broglie length associated with this particle. If you have some interaction in the dark sector, dark matter that talks with dark energy, there will be again an interaction term, right? There will be a coupling term. So you need to bring a number into the system. And actually, as I say, always say, you name it dark matter, right? I think there are more models for dark matter in the world than people working on them. But there is an elephant in the room. And the elephant in the room, in my opinion, it cannot be neglected. And the elephant in the room, it's galaxy formation. When we compare galaxies observed and dark matter simulations, we are making a huge assumption, right? We are making the assumption that whatever happens while you produce stars, gas collapsing, cooling, does not affect the properties of dark matter. Is this the case? So in order to answer this question, what one has to do is to work with hydrodynamic simulation. That's what we've been doing in several years, from starting 2010 with the projects called First Magic and now into NIHAO. NIHAO, it's our database of simulations. It's an acronym, stands for Numerical Investigation of 100 Astrophysical Objects. And it's an acronym, means hello in Chinese. And that's a list of the conspirators, the people working on this project. So what is NIHAO? NIHAO is a set of very high resolution for simulations of galaxy formation. The idea of the project is that to resolve any object from a dwarf galaxy up to a massive elliptical, always with the same number of elements, always with at least 1 million particles. So you don't have to worry that when you look at the dwarf galaxy or the Milky Way galaxies, you can resolve, you can always resolve the same fraction of the via radius of the scale length of the disk. Okay, what you see on the right is one of the movie from one of our own galaxy that shows we have been able successfully to reproduce very thin stellar disks. And on the left, you see the list of all the things we have in our simulations. Without going into details, we have all the usual suspects: supernova feedback, massive stars feedback, black hole accretion, AGN feedback, local photonization, so far, so on. So the point of NIHAO is that at the same time, we can resolve the collapse of dark matter. That's the same movie you saw at the beginning on the left. But in the meantime, we are tracing gas accretion, gas temperature. That's a central movie where gas is color-coded by temperature, red, hot, blue, or white cold. And we're also tracing star formation that you see in the last plot on the right. For example, now you see a satellite. It's coming, it's being accreted, and it's being destroyed. That's very clear in the star plot, and you see that the same thing is happening in dark matter, gas, and stars. So with NIHAO, we've been very successful in reproducing very realistic gases. What you see here is on the left, or I'm not sure how the screen is oriented, so it's left if you're facing the screen as I do, you have real galaxies, and on the right, you see the NIHAO counterparts. You see the NIHAO has been very successful in reproducing merging galaxies, top left, thin disks, grand design spirals, so far, so on. The reason that we have more than 200 galaxies in the database. There is a caveat that will become important later, that when we do dark matter only simulation, we can do things from first principle. We know the gravitational law and we can trace it. When it comes to hydro simulation, so when you have gas and stars, you cannot do things from first principle. Why is that? Well, the reason is that look at how in galaxy star formation is implemented in this kind of simulation. And this is true across all codes. It could be fire, millennium, doesn't really matter. We all do the same thing. You have a gas element, which we call particles, which has a mass of 10 to the 4 solar masses. When this gas element has the correct temperature and temperature and density, we allow it to make a star. What happens is that part of the mass of the gas particle stays as gas, and part of it is converted into stars. So when I say stars, I mean a stellar cluster of several thousands of solar masses. Now, part of the stellar cluster will be made of massive stars. Those massive stars will explode as supernova, and then we release some supernova energy. This energy is fed back into the gas, and the gas, which is at some temperature and density, will move to a new temperature and new density under the field. Now, what is the problem? The problem is that this is a picture of star formation. That's a famous picture from the Hubble Space Telescope. What you see here are very young stars, those are blue points in the center of the image. They're tearing apart the cloud that was the birth cloud of the stars themselves. Now, this beautiful physics is encapsulated in one of our gigantic particles. So we cannot do things from first principle. We have to make assumptions and some shortcuts. So one thing we have to do, since we cannot do things from first principle, is to validate simulations against observations. So one relation that we use intensively is the stellar mass-LO mass relation. So if you look at the plot on the right, you have on the X the total mass of the galaxy, which can be measured through gravitational lensing, satellites dynamics. There are many ways. And on the Y, what you have is the stellar mass of the galaxy. Real galaxies, they live around this black line with the gray band around it. And the blue points are the NIHAO galaxies. So NIHAO has been tuned in order to reproduce this relation. So it's done extremely well across almost 5 orders of magnitude in stellar mass. Of course, you also want to test against other relations. On the left, you have the Tully-Fisher relation, stellar mass versus velocity. And again, you have observations in red and NIHAO in black. And you see that NIHAO can get normalization, 0 point, and scatter of the relation. The same applies to cold gas, for example, on the right, where you have the mass in cold gas versus the size of the gaseous disk. And again, NIHAO nails down scatter, slope, and 0 point. So there is a plethora of NIHAO papers. We use the Roman numbers to number them. And the last one is NIHAO 28. So what NIHAO then allows us is now we can compare real and simulated galaxies on the same ground. So what happens to the self-similarity? Let me go back to this plot. The blue line, the blue dots is the rotation curve of a famous galaxy, IC 2574, which is famous because it's extremely difficult to be fitted in cold dark matter. Because the cold dark matter fit is the green line with the area around it. As I told you before, this galaxy has a very slow rising rotation curve. And so it's very hard, if not impossible, to fit it within the cold dark matter frame. What happens when you add baryons to this kind of simulation? Well, that's what you get. What you have here, it's one of the NIHAO galaxies compared to IC 2574. The blue points on the left and the red points with arrow bars on the right, they belong to the same galaxies, just 2 different sets of observations. And what do you have here? So what you have here, this is the profile that we get if we run the galaxy without baryons. That's a black line. It's the same as before, the usual NFW-like rotation curve. But when we add baryons, that's the rotation curves we get. That goes amazingly through the whole plot. That means that self-similarity can be broken by galaxy formation. We can take a rotation curve which is stiff and flatten it down. And self-similarity, it's broken in all possible ways. What you see in the right plot is like the sum of the breaking self-similarity. You have, as a function of radius, x-axis, you have the ratio of the rotation curve in the simulation with the hydro, so the galaxy formation, and without. If self-similarity would not be broken, we would expect all those different curves. Here, each curve is a different galaxy, and the color coding depends on the stellar mass. We would expect all galaxies to flatten around 1, right? It's still self-similar, so the rotation curves would be one on top of the other. What you see here instead is that self-similarity is broken, and it's broken in a sort of a fun way, right? Galaxies, they go above and below. So not only we break self-similarity, but we break in different directions. How is that possible? Well, the reason is quite simple, has been nicely summarized in a beautiful work by Ponson and Governato in 2015. What you see here is the gas distribution in a galaxy of around 10 to 11 solar masses. What you see here is that the gas is everything but steady, right? It's accreting to the center to gravity, and then it's pushed out through supernova explosions. So the gas is going in under gravity and going out under supernova explosions. Why is dark matter moving around when that happens? Well, dark matter is reacting to the gravitational potential. So when the gas goes in, dark matter follows. The gravitational potential is deeper, and dark matter moves in. When the gas moves out, dark matter follows as well, right? The gravitational potential is shallower, dark matter will relax. What you can see here is there's this two phenomena, the infall and the outfall of gas. They happen on very different timescales. That's very clear, especially if I rewind the movie. The falling of gas happens on free fall timescale. The expulsion of gas is almost instantaneous compared to dynamical time in dark matter. This means that even if I have the same amount of gas going in and out, the net effect of the two processes is not cancellation, because one infall happens in an adiabatic way, where the outfall happens in a non-adiabatic way from the point of view of the dark matter. As we all know from physics 1, a non-adiabatic process, they win over adiabatic process, right? They will disperse, generate more entropy into the system. So what's happening here is that dark matter is reacting to baryonic infall, and the net effect in most of the galaxies is an outward moving of dark matter. What is more important that you can imagine that each galaxy has its own history of gas infall and outflow. And that's why self-similarity is broken. It's broken all over the place. So one effect of this breaking of self-similarity, there's no such a thing as a universal density profile anymore, which is very interesting for people that look, for example, for dark matter annihilation or direct detection. So one way to characterize the profile of dark matter is to use the slope, the asymptotic slope of the profile. So if you have a dark matter halo and it follows the Navarro-Franken-White profile, if you look at the slope in the log-log plot of the density profile, it goes like alpha, and alpha is roughly -1. That's just asymptotic slope for Navarro-Franken-White. If you put baryons and if you plot alpha on the x-axis versus the mass of the halo, you see it's all over the place. Right? That's what would you expect in a nice cold dark matter universe where self-similarity was not broken. It's roughly the same profile. It's slightly bent because of the concentration parameter. But it's roughly the same number for all halos. What you see here, it changes widely between -2, strong contraction, up to 0. And here the points are color-coded red. The galaxies, they are mainly dominated in the inflow-outflow of the gas by supernova explosions. And in blue, you have galaxies that are mainly dominated by AGN field. So even feedback from black hole, which is moving gas in and out, has an effect on dark matter distribution. Okay? So what you see is that self-similarity is broken. And it's also broken when it comes to the satellites, right? I told you that another problem is that different kind of galaxies have different number of satellites around them. The same happens when you look at the number of satellites. So what you have here is, as a function of stellar mass of the satellites, what is expected from observations. There are two lines here. The black bottom one is the Milky Way. And you see the names of the satellite, like from highest mass to lowest, Large Magellanic Clouds, Small Magellanic Clouds, and keep going. And then on top, you see the same plot for Andromeda. And now what you see here, those are 4 of the Nihao simulations at the highest resolution in order to resolve the satellites. And you see they're nicely bracketed by the observations. This means that we are able also to break the self-similarity in the stars. Why is that? Well, the reason is that if you compare the dark matter distribution on the left and the stellar distribution on the right, you can see that not every single satellite in dark matter has a stellar counterpart. And this is because star formation is an extremely inefficient process. You have supernova explosion, you have the UV background from the other stars, you have ram pressure. There are a lot of phenomena that will prevent gas to be accreted and make stars in small satellites. And so while on the left, you can count easily tens of satellites, on the right, you'll see that only the most massive ones, for example, the satellite which is incoming now from left to right, there will be another one coming from the bottom in a second. Only the big there it goes. Only the big satellites have a stellar counterpart. The small ones are mostly dark. So self-similarity is broken also for the satellites. That's a way to quantify that. What you see here is that as a function of the halo mass, the stellar mass of satellites, and you see you have points that have stellar mass, and you have this bunch of points on the bottom that have zero stellar mass. They've been put at 10 to the 3 just for visualization. And the magenta, the purple line tells you the fraction of dark satellites. You see that if you cross 10 to the 9, most of the satellites are dark. Self-similarity is broken. So now I can go back to my initial picture, and usually in a normal talk, I will ask people to guess the mass of this object. Since this is online, I'll tell you. This halo here is the host of one of the smallest galaxies we can produce in NIHAO. This object has a total halo mass of 10 to the 9, and the mass in stellar mass is below 10 to the 4. This is one of the smallest galaxies. And now you see self-similarity broken at its best. On the big dark matter map on the left, only the tiny part in the center is populated with galaxies. So is everything solved in galaxy formation? Am I claiming that we know everything? Well, no, not at all, right? This is a very nice compilation of galactic properties. What you see here is a set of properties. For example, on the top right, you have stellar mass versus rotation velocity. That's a Tully-Fisher relation. And what you have a gray cloud. Those are results from the MANGA survey. And in pink stars, you have NIHAO results. And you see NIHAO does very well to fit the scaling relation. I think some of them, like the Tully-Fisher, amazingly well. But there is a bunch of relations where NIHAO fails, right? For example, if you look at the bottom right, that's one of the worst, the star formation rate, stellar mass, and you see that the magenta points are not in the bulk of the observational data. But those are problems due to our inability to resolve galaxy formation. Remember, I told you we use a gigantic particle to capture amazing physics, right? And hence, what does it mean? It means that all the problems that are left in galaxy formation are on the luminous side, not on the dark side. Despite that, there are always new issues. There are always new papers, one per month, that come with the challenge and inexplicable new observations. They want to prove dark matter wrong. For example, there's been recently claims of the resistance of galaxy without dark matter. It took 2 years to my group and other group in Harvard to show that those galaxies occur naturally in galaxy. There's the plane of satellites. And again, in the last 5 or 6 years, we have shown, us and other groups, that this is completely, it's very easy, it can be explained within cold dark matter. So I think that my conclusion is that at the moment, there is no observational evidence that is forcing us to move away from cold dark matter. And all the discrepancies between cold dark matter, for example, some residual diversity in rotation curves, are mostly linked to our inability to fully simulate galaxy formation. That brings me to my last 2 slides. Is then cold dark matter the answer? Well, actually, the answer is no. Because from the point of view of galaxy formation, we can't say anything on the actual mass of the dark matter. When I talk about cold dark matter, I'm not saying WIMPs. I'm saying that anything with a mass larger than 5 keV, remember WIMPs are on the G scale, it's fine if it's a thermal candidate. If you remove the condition to be a thermal candidate, for example, axion dark matter is perfectly fine as well. So an axion with the mass of 10 to the minus 12 electron volt will have the exact same property as a cold dark matter particle of GeV mass for galaxy formation. So this is telling what I want to tell you is that cold dark matter is not wrong, but this does not mean is that the right model. And actually, the fact that baryons can break the self-similarity is telling us that it will be harder and harder in the future to learn anything about cold dark matter by galaxies. Thank you very much for your attention. And it's 24:48 at my clock. Thank you very much.
Perfect. Okay, nice talk, entertaining. Surely there are questions or comments. Please.
Thanks for the interesting talk. Going back to that rotation curves fit you have shown about that inclusion of variance in the NIHAO simulation help to fit that particular galaxy's rotation curve. So I wonder, like,
no, that's but sorry.
Is this one?
No, that was not the goal, right? When we ran NIHAO, we didn't want to reproduce IC2574. The point is that if you run 200 galaxies, you will sooner or later find something that resembles IC2574. Okay, and that's because the diversity it's broken all over the place.
Yes, so the galaxy that is identical to that has been taken to. Sorry, did I understand correctly? So for that particular galaxy that has been observed, so from the simulation, you select the galaxy which is the most identical to that, and you compare the rotation curve.
Correct.
Would it be better to look at the stacked rotation curves across like a variety of galaxies rather than looking at individual galaxy?
Absolutely. This has been done in a set of papers by one of our students, Isabella Santos. It's one of the infinite NIHAO papers I was showing before. Yes, this is one example, but we have a statistical study of that. Yes, stacked and also using specific points of rotation curve. This has been done and the agreement is very well. It's very good. It's not perfect, but I think what is left, we can be blamed on cold dark matter. Most likely it's blamed on our inability to resolve galaxy formation at the core.
Yes, thanks.
Welcome.
Yes, please.
I'm curious why you picked the number 10 to the minus 12 for axion-like particles. Wouldn't a 10 to the minus 16 or even a 10 to the minus 18 look exactly like cold dark matter?
Anything that is above 10 to the minus 20 will look exactly as dark matter. You can pick the number that you most like.
Okay, thanks.
Which is sad, right? It means we have no handle. We can't tell anything. I'm very worried about that. I have another talk that says that we're not going to learn anything about dark matter in the next 20 years. But I didn't want that to be recorded.
Okay, we'll scratch that part. I like the rogues gallery that you showed of simulations and true galaxies, and I'm just wondering how hard you had to work to make that rogues gallery, and how did you do it? Did you just simulate hundreds of galaxies and then you looked at the NGC catalog for matches, or did you do it the other way around?
The first way. So the point of NIHAO was to be completely unbiased. So we select 100 galaxies initially. Now it's 200. The only request, we didn't want mergers at redshift 0, which didn't really happen, right? Because if you look, one of the galaxies did develop a merger in the Hydra run. The only request was no merging galaxies at redshift 0. So it's very unbiased. All possible environments, all possible halo masses, and it just happens. If you have 100 galaxies, I mean, galaxies are different, but not that different one from each other, right? Okay, here, of course, there's some cosmetics. We oriented it in the exact light weights in order to make it, this is not supposed to be a quantitative, but it just happened.
Including the very thin disks. I mean, I think that's impressive. It wasn't so many years ago that there was some concern that Lambda CDM couldn't produce spirals with thin enough disks.
That's exactly correct. So the first question that we wanted to answer is that can we produce a proper disk galaxy in Lambda CDM? That was the driving question for NIHAO. Then all the rest are kind of auxiliary. And the answer is yes. And I want to be honest, we are not the one who solved the problem, neither first nor at the best, most likely. There is a consensus in the simulation community that forming disks in Lambda CDM is not an issue anymore. It's a combination of baryonic feedback and numerical resolution.
Okay, well, let's thank the speaker again.
Thank you. Promise to come in person next time.
Yep, thank you. And I guess this is the end of the session. We're back to coffee.